Welcome to this tutorial on using ROS2 with MATLAB and Simulink. Here's the learning path we'll be following throughout this tutorial. In this session, we will focus on another core concept of ROS2, the ROS2 topic. Let's take a closer look at the detailed outline for today's session. What is ROS2 topic? We'll begin by understanding what a ROS2 topic is and its role in the ROS2 ecosystem. Publisher and subscriber in MATLAB. We'll explore how to create and manage publishers and subscribers using MATLAB, allowing you to send and receive data efficiently. Customize message definition. We'll explore how to customize message definitions to suit your specific application needs, ensuring the data exchange. Publisher and subscriber in Simulink. We'll then transition to Simulink, demonstrating how to set up publishers and subscribers. Quality of service, QoS. Finally, we'll discuss quality of service settings, explaining how they can be configured to optimize communication reliability and performance. What is a ROS2 topic? A ROS2 topic is a fundamental mechanism used for exchanging data among ROS nodes. It acts as a channel through which nodes can communicate by sending and receiving messages. In this setup, a publisher node is responsible for publishing messages to a topic, while a subscriber node listens to that topic to receive the messages. This publish-subscribe model enables decoupled communication, allowing nodes to interact without needing to know about each other's existence. It's important to define your ROS2 topics carefully to ensure efficient and effective data exchange within your robotic system. Understanding this concept is key to harnessing the power of ROS2 in your projects. ROS2 topics offer flexible communication patterns that can be adapted to various system architectures. These patterns include one-to-one, one-to-many, and many-to-one. The pattern of the ROS2 topic can also be many-to-many. In ROS2, messages are defined using a simple yet powerful data structure format known as .msg files. These files allow you to specify the structure of the data that will be exchanged between nodes. A message file contains fields, each with a specific data type such as integers, floats, or strings. You can also define arrays and complex custom data types to suit the needs of your application. This flexibility ensures that you can tailor message definitions to match the specific data requirements of your robotic system. By customizing .msg files, you can tailor the message content to fit the specific needs of your application. Next, we will move on to creating ROS2 publishers and subscribers in MATLAB. Let's begin with a Hello World project to understand the publisher and subscriber in ROS2. First, we create a ROS2 node called Node Publisher. Next, we create a publisher for a topic named Hello, using a message type of string. The publisher's properties include not only the topic name, message type, and the ROS2 node's name, but also additional attributes such as history and depth. We'll revisit these aspects later in the Quality of Service QoS session. Next, we create a ROS2 message and assign the string Hello World to its data field. When we list all the available topics in the ROS2 network, the Hello topic will be included. We will then configure the execution rate for the ROS2 node. In this example, the desired rate is set to 1 Hz. Next, we initiate a for loop to send the message through the publisher every second. Okay, let's set up a subscriber. We create a ROS2 node called node subscriber. Then we set up a subscriber using the topic name from the publisher and the message type. In MATLAB, there are two ways to subscribe to a topic: blocking mode and non-blocking mode. In blocking mode, the subscriber waits and blocks MATLAB until it receives a message or times out. In non-blocking mode, when the subscriber detects an incoming message, it triggers the callback function. In this example, the callback function will display the message data without blocking MATLAB execution. Let's explore another example using a webcam, where we will demonstrate how to publish and subscribe to video streams. Note that we will launch two MATLAB instances, one for the publisher and the other for the subscriber. First, we create a ROS2 node called Node Publisher. We also create a publisher for a topic named Webcam, using a message type of image. Next, we create a ROS2 message linked to the publisher. Next, we list all available webcams and select an appropriate one. We then specify an execution rate for the ROS2 node. In this example, the desired rate is 5 Hz. After that, we start a for loop. In each iteration, the loop acquires an image from the webcam, assigns it to the message, and publishes it through the publisher. On the other hand, from another MATLAB instance, we create a ROS2 node and a subscriber to receive the image. When listing the ROS2 topics, we should be able to find a topic named Webcam. We create a subscriber using the topic name from the publisher. In this example, we will use a non-blocking mode subscriber with a callback function, which reads the received message, converts it to the MATLAB image format, and displays the image during runtime. Let's explore another example using TurtleSim. First, we launch TurtleSim from Ubuntu. On the MATLAB side, we create a ROS2 node and list all available topics with their message types. We can see there is a command velocity topic and a pose topic. We can also see their associated message types. Next, we explore the data structure of the message types. For the twist message, we observe the linear velocity and angular velocity in its data field. Each velocity is represented as a three-dimensional vector containing x, y, and z components in 64-bit float format. If we attempt to explore the data structure of the TurtleSim/pose message type, we encounter an error, indicating that this message type is not recognized in MATLAB. When listing all available message types in MATLAB, the TurtleSim/pose message type will not be found. We will revisit this topic later in the session on customizing message definitions. Okay, now we create a publisher to send linear and angular velocity commands to the turtle. We create a message linked to the publisher and assign the appropriate values to it. We then specify an execution rate for the ROS2 node. In this example, the desired rate is 1 Hz. We start a for loop to publish the commands. We can see the turtle following a circular path. If we modify the linear velocity command and publish it again, we will see the turtle follow a different circular path. Next, we will move on to customizing message definitions in MATLAB. Let's recap the previous example with TurtleSim. When we attempted to explore the data structure of TurtleSim/pose, we encountered an error indicating that this message type is unrecognized in MATLAB, and it is not listed among the available message types. To resolve this, we can create custom messages. First, create a folder named Custom. Inside it, create a TurtleSim folder, and within that, a MSG folder. Then, create a .msg file and define the data structure within it. To determine the data structure for the .msg file, you can use the ROS2 interface show command in Ubuntu to inspect the message definition. Now, we can generate the custom messages defined in the .msg file. Once the compilation process is complete, we can verify the successful generation of the message type by listing and locating it among the available message types in MATLAB. We can also double-check to ensure that the message definition is correct. Now we can create a subscriber to subscribe to the Turtle1/pose topic, which uses the TurtleSim/pose message type. Next, we will move on to creating ROS2 publishers and subscribers in Simulink. Let's open the Simulink model for a TurtleSim example. There is a message block where you can select the appropriate message type and set the sample time. We then feed the message value to the bus assignment block, which specifies the linear velocity command on the x-axis and the angular velocity command on the z-axis. Additionally, there's a publisher block where you can select the topic by its name. When running the Simulink model alongside TurtleSim in Ubuntu, we can observe the turtle following a circular path. Let's open another Simulink model for a TurtleSim example, which not only publishes the command but also subscribes to the pose of the turtle for path-following feedback control. In this model, we have a message block, a publisher block, and a subscriber block. There is also a path-following block that implements a path-following algorithm called pure pursuit. Another Simulink block generates the desired trajectory. When running the Simulink model alongside TurtleSim and Ubuntu, we can see the turtle following the desired path. Note that in Simulink, simulation pacing is enabled to 1, meaning the Simulink model runs in real time while the TurtleSim runs in real time as well in Ubuntu. This synchronization ensures that the two ROS nodes run in parallel. We will revisit this topic later in this tutorial. Next, let's move on to the final session, Quality of Service, QoS. ROS2 offers a rich variety of quality of service QoS policies that allow you to tune communication between nodes. With the right set of quality of service policies, ROS2 can be as reliable as TCP or as best effort as UDP, with many possible states in between. Unlike ROS1, which primarily only supported TCP, ROS2 benefits from the flexibility of the underlying DDS transport in environments with lossy wireless networks, where a best effort policy would be more suitable, or in real-time computing systems where the right quality of service profile is needed to meet deadlines. In the following session, we will walk through some of the QoS policies. Let's start with the concepts of history and depth. A publisher sends a message to a subscriber, but the subscriber requires some time to process the message. Imagine the publisher is sending a large number of messages, which accumulate in a queue on the subscriber's side. If the history is set to keep all, the ROS2 network will store all samples, subject to the configured resource limits of the underlying middleware. This is crucial when it is important to process every message. If the history is set to keep last, the ROS2 network will store only the most recent samples, with the number determined by the configurable queue depth option. For example, if the depth is set to 2, the queue will retain only the last 2 messages. Next, we will explore the concept of reliability. The reliability. QoS policy determines whether the delivery of messages is guaranteed in the presence of networking issues. If dropped messages could have an impact, it is advisable to set the reliability to reliable, which ensures that samples are delivered and may involve multiple retries. If dropped messages are acceptable and you want to avoid impacting the performance, it is advisable to set the reliability to best effort. This setting attempts to deliver samples but may lose them if the network is not robust. Next, we will explore the concept of durability. The durability. QoS policy controls the persistence of messages for late joining connections. When durability is set to transient local for a publisher, messages that have already been sent are maintained. If a subscriber with transient local durability joins the network later, the publisher will send the persisted messages to the subscriber. In this example, with the depth set to 2, the late joining subscriber will receive the last 2 messages from the publisher. When durability is set to volatile, publishers do not persist messages after sending them, and subscribers do not request persisted messages from publishers. Please note that the depth defined in the publisher should be equal to or larger than that of the subscriber. For messages to pass between 2 communication objects, their QoS policies must be compatible. We will revisit this topic later in this session. Next, we will explore the concept of deadline. The deadline. QoS policy defines the expected interval for publishing consecutive messages to a topic, setting the maximum duration allowed between messages. For subscribers, it specifies the permissible duration between message receptions, while for publishers, it indicates the allowed duration between message transmissions. If the deadline QoS policy is not set by the user, it indicates an unspecified duration, which the underlying middleware typically interprets as infinite. Next, we will explore the concept of lifespan. The lifespan QoS policy defines the maximum duration a message can exist between being published and received before it is considered stale or expired. It sets the validity period for a message. For subscriptions, it specifies the duration a message is considered valid, beyond which it will not be received. For publishers, it determines the time frame during which a message is considered valid. After this period, the message will be deleted from the topic history and will no longer be sent to subscribers. Expired messages are silently discarded. If the lifespan QoS policy is not set by the user, it indicates an unspecified duration, which the underlying middleware typically interprets as infinite. Next, we will explore the concepts of liveliness and least duration. The liveliness. QoS policy defines the protocol for entities to declare their liveliness status. If liveliness is set to automatic, the system will consider all of the node's publishers to be alive for another least duration whenever any one of its publishers publishes a message. If liveliness is set to manual, the system will consider the publisher to be alive for another least duration only if it manually asserts its liveliness through a call to the publisher API. Next, we will explore the QoS compatibility. Here is a compatibility matrix that summarizes the QoS settings. Please pause the video to take a look. We will examine an example that showcases an incompatible QoS policy, the deadline. This policy represents the expected maximum amount of time between consecutive messages being published to a topic. For the deadline QoS policy, the publisher's deadline should be less than or equal to the subscriber's. In this example, we will demonstrate a counterexample where the publisher's deadline is, by default, infinite, which is greater than the subscriber's deadline of 1 second. When we create the subscriber, MATLAB will display a warning message indicating the incompatibility of the deadline QoS policy. We can also capture the QoS incompatibility event by defining an incompatible QoS callback function, which displays associated information when the event occurs. We will explore more examples of QoS events later in this session. As mentioned, let's explore two more examples related to QoS events. Let's take a look at this example, which showcases the QoS event of missing the deadline. We create a publisher with the deadline QoS set to 1 second. However, the ROS2 node running the publisher executes every 5 seconds. In this case, the publishing deadline will be missed, triggering the deadline missed QoS event callback function. Let's examine another example that demonstrates the QoS event of message loss. In this example, we launched two MATLAB instances, one for running the publisher and the other for running the subscriber. The publisher sends large-sized message data continuously, as fast as possible, with the reliability QoS policy set to best effort. This setup triggers the event of message loss, causing some messages to be lost in the process. Consequently, the subscriber fails to receive all the messages. Okay, hopefully, you now have a better understanding of these QoS policies and events. It's always beneficial to engage in hands-on exercises to explore and comprehend them further. I hope you now have a solid understanding of ROS2 topics, messages, quality of service, and how to create publishers and subscribers in both MATLAB and Simulink. Thank you for participating in this session. In the next session, we will explore the ROS2 service. By the end of the session, you will have learned about service server and service client in ROS2. I look forward to our next session together.